Alrighty, so this is going to be our wrap up for sigma notation, summation notation. Just want to do two last quick examples just to illustrate and remind people about what sigma is. So when we look at a sigma notation expression like this, it's a great way to represent or give a rule for a series without having to write the entire series out. So the number on the bottom again is the starting term number. So we're going to start at term number 1. The number up top is the ending term number. In this case, it's an infinite series. So you couldn't actually write the whole series. It goes on infinitely. And then the expression that comes after this is our AN. This is representing the nth term. It's how we generate the terms in the series. So for our first term, which is where we're starting, I would substitute in 1 for k, and I can evaluate and find that first term in the series. And if I want to find term 2, I substitute in term 2. If I want to find term 3, put in term 3, and so on. Now, when we talk about infinite series, again, I can't necessarily write the whole, well, I can't write the whole series, but I need to show enough so people can tell what the series is doing. So 2 terms really isn't enough to see a pattern because there's so many different ways you can get from one number to the next. So make sure you do at least 3 in an expanded infinite so people can tell who are looking at that series what you're doing. So the first term then, anything to the 0 power is 1, so 1 times 3. And then 1 half to the first times 3 would be 3 halves, or if you want 1.5, that's fine. Instead of doing the arithmetic though, remember, you know that this rule, I should have talked about that, that rule is an exponential equation. And because it's exponential in my series lingo, that means it's geometric. And take a look, with this geometric, it has a ratio or an R of 1/2. That's really critical as we look at what kind of series this is. So what are these terms doing? Well, already we can see what's happening. They're getting smaller. I'm multiplying by 1/2. So these terms get smaller and smaller and smaller. The limit exists. They approach 0. Again, critical when we start talking about what we do for our sum. So if you want to get to the next term now, you can go ahead and do this arithmetic. So it would be to the second, so 1/2 squared would be 1/4, and then times 3. Or you can just multiply the second term by 1/2 because we know that's what our ratio is, and we would get our 3/4. Whichever way makes more sense to you. And then again, plus dot dot dot. This is an infinite series. It's not just these first 3 terms. It's infinitely many of them. All right, now, can we do a sum? The actual notation sigma means sum. We want to make sure we do the sum. Infinite kind of seems crazy to even think about that. How can you add up an infinite number of things over time? Because if they continue to grow, we're not going to be able to do that. But this is geometric with the ratio being 1/2. Ooh, that was cool. Look at how that flew all the way over there. That has never happened before. Woo, there it goes. That is really cool. I've never done that before. Sweet. That's really neat. Anyway, so sorry, a little aside. So when you think about what those terms are doing, they're getting smaller and smaller. They're going towards 0. That's the only kind of infinite series we can actually find the sum for. Geometric ratio less than 1, because the limit goes to 0. The terms get really, really small. And if you remember, looking over a little thinking bubble here, we actually have a formula for that. We did the limit of that geometric series formula and came up with our A1, which is 3, over 1 minus the ratio. So it would be 3 divided by 1/2, or 6. So the sum of that infinite series, if I could add up 3 plus 3 halves plus 3/4 and so on, if I could do that infinitely many times, I would get closer and closer to 6. All right, cool. That's sigma notation. Now we're going to go the other direction. We spent a lot of time in day 1 looking at models that were more familiar to us, arithmetic, geometric. We even did a factorial, but there's lots of other ways that things can grow. So I want to do one last example with you to model something that's not arithmetic, it's not geometric. Can we come up with what this growth model would look like? So taking a look at what these numbers are doing. And they are definitely growing. And it's a finite series because it does end someplace. So my kind of strategy here is to try to line up different kinds of models that I know. So other things we talked about were quadratic, which we did an example like yesterday, and cubic. So I want you to think about the perfect cubes here on this one. Perfect cubes. So the first perfect cube is 1. I don't see anything here that really looks like 1. The second perfect cube is 8, which is kind of close to 10. It's not exactly, but it's kind of close. So when I can find a number that's kind of close, I try to see if I can find something that pattern could continue. What's the next perfect cube after 8? It's 27, right? 3 cubed. And then the next one after that is 4 cubed and 5 cubed. And I bet you maybe didn't know 6 cubed off the top of your head, but it's 216. And then up to 10 cubed, which is 1,000. all of these numbers that I wrote in green underneath, it's almost exactly the same series. They're just too small. So if I take a cubed number and add 2, I'll be able to get to that value. So it's looking to me like this rule is n cubed plus 2. Perfect cubes. Now we have to figure out where we're starting though. So what cubed did I need first to get to this 8? Well, I needed 2. So how about start at term 2? And then how do I figure out the top number? Well, some people can just kind of look. I didn't show the whole sequence, so you can't just add them up and figure it out. But this is term 2, 3, 4, 5, 6, or some in the middle. I need to get to this one. Or remember, you can just set your last term equal to your rule, and you can solve. So that would be 1,000 equals n cubed. So n must be 10. So if you're not sure, we can use the rule, we can get that. Now that's fantastic. I think that's the easiest way to do this one. So I'm looking for patterns of numbers that are at least close to the ones I have, and then I can make that adjustment just like we did for the linear ones before. It's just a lot harder when they're not something that we use frequently. What if I wanted to start at term number 1? How would my rule change? Well, if I started at term 1, that means I would have to end 1 less, so I'd be ending at term 9. I still have to cube something. This still has to be something cubed. And it still has to be adding 2 because it's going to be 2 off. But what would you have to do? You couldn't use n. If this were just n, that would be only 1 cubed. I need 2 cubed. So how do I make 2 cubed if I'm starting with a 1? Well, add 1. So I'm off by 1. If I back it down 1, I need to add that 1 back in somewhere. So if I put in n equals 1, 1 plus 1 is 2, 2 cubed is 8, and I'm off to the races. So when I look at these, I can make adjustments. Remember, there's infinitely many ways you can write them. But the whole idea is that we're able to express a series in this sigma notation. Some of them are tricky, though, and practice really helps for these. So try not to get too frustrated if you can't see something right away. The more you do of them, the easier it is to recognize, and there's still going to be ones that are going to be a little bit tricky. All right, so sigma notation.